Okay, welcome to this post-coffee session. The next talk will be by Professor Vandana Nanal, who is in the Department of Nuclear and Atomic Physics in TIFR, and she will tell you about Neutrino-less double beta decay and about tintin.
Thank you. And it's nice to be here. Thanks to the organizers for inviting me. And this probably is the only familiar figure you will see in this part, because I will be talking completely from the different experimental aspects and experimental point of view. So I'm not going to be talking about the theory, but this is the kind of you start off with the right figure for the Neutrino-less double beta decay experiment. So what I want to do is, I am a nuclear physicist, so I will now look at this problem from the nuclear physicist point of view, and then what are the ways, what are the techniques that go in different experiments, and then so give some idea about different experiments, where the field stands today, and the flavor of the Indian efforts. So you all have been talking about beyond standard model and are well aware of neutrino, but since I want to start at the beginning, let me start from before the days of standard model. So let's start with the beta decay and birth of neutrino. As you all know that there are nucleus, which consists of a few neutrons and protons, are strongly bound systems, but not all nuclei are stable, and some of them, some combinations decay into the others. So which you have the same mass number, we will refer to them as isobars. We also know that neutron is slightly heavier than proton, so even a free neutron decays into proton and electron with about 10 minutes half-life. And this is what is a process which essentially happens inside the nuclear beta decay. And the puzzle of the continuous electron spectrum, because if it was electron was the only particle coming out, should have had a simple energy, say a simple monochromatic electron, but with the continuous spectrum gave to the birth of the concept of neutrino, and I'm sure in all this time you have looked at all of this. So Pauli proposed in 1930 and Fermi developed the beta decay theory. So the looking back, and this is again something which you are familiar about, the open question still is a neutrino its own antiparticle or not? Is it a Majorana or a Dirac particle? Because if neutrino is massless, the helicity will be a good quantum number. So if what is originally thought of is the standard model is that you have a left-handed neutrinos and right-handed antineutrinos. So this is an open question which we are looking. I don't know how many of you can recognize from this picture, but you'll find the hint in the slide. So beta decay told us about neutrinos. So now we go to double beta decay to understand about the nature. So what is this double beta decay? That means the two neutrons inside a nucleus simultaneously have to change into two protons. And so this is obviously a second order weak interaction process, so much hindered, much less probable. And when can this happen? When the single beta decay is forbidden. Now, when that happens, it can either be a forbidden because of energy, and I'll explain that in a minute, and or it can also be a spin forbidden. So let me explain the spin forbidden a little bit. We know that when the electron is emitted, it does, because of its very less mass, it can carry a very less angular momentum. So if the nuclear transition is between the states where there is a large amount of spin change, then there has to be a large amount of orbital angular momentum to be carried out by electron, and that probability is much hindered. And this happens in two nuclei, zirconium-96 and calcium-48. Remember it, I'll ask you at the end about it. So that, but the first time, it was Maria Goeppert-Mayer, whom you see here and who received Nobel Prize for nuclear shell model. In 1935, suggested that such a process also can happen, and she even estimated the half-life for it, which was 10 power 17 years. Of course, today you have a better estimate, but what she did. By the way, incidentally, I just want to say she liked doing things with two. She even did the two-photon excitation today, which is forms the basis of nonlinear photonics. But the observation, because it's a very rare process, the first evidence for this was obtained around in 1950, and this was a geochemical observation. In the ores, they found the concentration of certain amount of 130 tellurium, and from that, a half-life limit was put. The first laboratory experiment, which is where you actually detect the two electrons coming out in the double beta decay, was happened in 1987 by Elliott's group, and Elliott is still active, working for germanium neutrino-less double beta. Now, most of you would have heard about the semi-empirical mass formula and the binding energy of nucleus. So what we have is the mass parabolas. So for a given isotope, given isobar A, you usually have the mass parabola. Now in nuclei, when there are even number of protons and even number of neutrons, they are extra stable because neutrons and protons like to pair with each other. So when you look at the mass parabolas for the even A, you have two parabolas because even A can come from a combination of even Z, even N, which lies lower because that means a higher binding energy, more tightly bound. When I say higher binding energy, that means it's a negative of binding energy. You have to supply that much energy to break. And the odd Z, odd N combination, which lies on top of it. When you talk of odd isobars, there is only a single parabola. And the nuclei which fall on this either side of the parabolic arms would like to go to the bottom of the well, and that's when you either get a beta plus decay or beta plus decay or beta minus decay to get to the lower point. So in this case there is no possibility because you can always that you will decay to the next next Z number or next N number and come to the bottom. But only for these even A nuclei, you have a possibility of that you can have a cascade like this, like which is shown here, that you start from this, go down here and come down. But now when one is sitting here, this guy cannot beta decay to iodine because it is energetically higher. So as I said initially, energy or spin forbidden. And this is more clearly illustrated in this parabola in a kind of expanded way. But what it can do is that if two neutrons decide to simultaneously convert, that's a double beta decay, it can come down and then get decay. So that's what makes some of these things as a double beta decay candidates. And similar, as we can say, beta decay has a beta plus electron capture counterparts, which are essentially similar processes happen here also. So you also have beta plus, you have beta minus EC and EC and so on. So you are looking for, in such a case, in a normal beta decay, you will have 4 particles which will be emitted. When I'm talking about beta minus, I will have 2 electrons and 2 electron antineutrinos coming out. So if you look at the mass parabolas of various nuclei, because binding energies are very well studied and we know this, so there are about 35 candidates where this can happen. And till today, only about 13 cases have actually double beta decay has been detected with a lifetime in the range of 10 power 18 to 10 power 24 years. Because this lifetime is also long because of the Q value, because this Q value is also has to be favorable because that will determine the decay rate. Now, of special interest to all of us is the neutrino-less double beta decay. Because soon after the concept of double beta decay was put forward, it was suggested by Raka that you can actually look for neutrino-less double beta decay. That is, if neutrino is its own antiparticle, you will only have a virtual exchange. And I'm sure there are more people here who know more details about the theoretical aspects of it. And then in that case, in the final state, you will only see 2 electrons. Now, if there are only 2 electrons coming out, individual energies of the electrons will be different. But if I sum up the total energy of these 2 electrons, it will be a monoenergetic. It will be same as a Q value. So if you can observe, you can detect these electrons, measure their total energy, and if that is like a delta peak as a single energy peak, not a continuous spectrum, you know that you are observing neutrino-less double. So the interest clearly is because that we can test the nature of neutrino, and you can also measure the effective Majorana mass. That is because the rate of the neutrino-less double beta decay will have a phase space factor. Since you have only 2 final particles in final state, 2 electrons, and there is a constraint on total energy, this goes as Q to the power 5. You also have the nuclear matrix element, and I'll say something about it later because this is also something which is quite uncertain. And then you have a term which is the effective neutrino mass. So by measuring this can be quite well calculated. This has calculations, some uncertainties, but you can get this. So, but whenever we are talking about neutrino-less double beta decay, a normal double beta decay would also happen. Even if neutrino is its own antiparticle, you will also have that. And in that case, you have 4 particles in the final state. So the rate will go as Q to the power 11. So even when you are looking for neutrino-less double beta decay, the background, the 2 nu 2 beta background also will be there. So this, when you look for NDBD, it is the rarest among the rare which you look. Okay, now with this background, which I think most of you already knew, so now I move on to how do we search for NDBD? How do we look for that? So as I said, there are about 35 candidates. So everybody who has a possibility of double beta decay should be possible to look for NDBD in that. But since it goes as q to the power 5, high q value is desirable. The other thing is, since it's a rare process, you will have to make very large detectors. So since you have to make large detectors, you need to have it abundantly available to you. So large isotopic abundance also is desirable. So this is what is plotted in this graph. You have a q value. So when I say q, it's the q2 beta, that is double beta decay q value, and the abundance. Now, what would have liked, one would have liked is something here, but nature is not that very kind to us. So 48 calcium has a highest q value, 4.6. And what I show here is all essentially which are above 2 MeV. Why that? That will become hopefully clear by the end of my talk, and if that is not, then we will come ask me and I'll explain. It's related to the background issues. But so the red ones are the ones which were some experiments are already going on, and even and some of the other isotopes also have been looked at. So you look at the q values which are above 2 MeV, so that you have hope of looking at the electrons in a little cleaner manner, and the isotopic abundance. Only tellurium has about 30% abundance, rest everything falls between 5 to 10. And what we are looking for is, we hope to measure something like this, and we will see when we plot the data. So what we have plotted here is the energy scaled with respect to q beta beta. So this is the q value. And if you look at the number of electrons emitted, this is your normal 2 nu beta beta, and this, if I see this peak, it will be correspond to the neutrino-less double beta decay. Or conversely, if the process is happening, this is what I want to detect. Now just remember, this is a cartoon, so relative ratios and everything is just very schematic. So what we will look for experimentally is the simultaneous emission of 2 electrons, because something is decaying and 2 electrons have to come out from a same vertex, a same physical location in the detector, and at the same point in time, and the constancy of the sum energy of the 2 emitted electrons. So this is what is known as the identification experiment. This will just give you identification. If I further want to study things, I have to measure those electrons, measure their energy spectrum, and so on. So that also can be planned, and people look at it, but that's there. So if I want to look at this sum energy peak, a tiny peak, if it is sharper, I can detect it faster, right? Signal to noise ratio. So this is why you need to necessarily a high resolution detector, high energy resolution detector. And because the event rates are very low, extremely low, you need to have a very large size source and detector. And that is the something which is will further look at. Now further, if we just see it in one isotope, we don't, it doesn't become conclusive. It's a good candle further to go, and or a good smoking gun to go further. So we also need to look at different isotopes, also from the point of view of the nuclear matrix element, because that also will have, that has an uncertainty of different elements. So depending on that, you will get a better, more reliable value of the effective neutrino mass. So now let's see further experimental considerations. So if I can, how do we make a detector? There are two types we can look at. Consider active source. That means my detector material itself is a double beta decay candidate, and therefore the DBD nuclear integral part of the detector. Other is the passive detect source. That means I have a detector and I have the source material. Now considering that you are talking about a large source sizes, which is a few hundreds of kgs to the few tons, if you have the passive type of a detector, your detector also itself becomes very massive along with the source. So you have a source plus you have a detection things, and when we have to reduce the backgrounds or take care of the purity, you have to take care of these multiple issues. So this is actually a preferred mode, though there is, this one gives you certain higher discrimination possibilities. So if you do an experiment and like you expect, you see a peak, very good, then you know how many counts you saw in the peak. That's the number of double neutrino-less double NDBD events you have observed. So you can then calculate your decay rate, you can calculate your mass and everything, assuming you get nuclear structure. But if you don't see it, if you don't observe it also, then you will be able to put a lower limit on your decay time, saying that it is half-life for such a process is larger than this number. And how will you arrive at that number? Because you're saying that your number, NDBD events is of the order of fluctuation in the background. So it's if I have background is n BKG, the event, the fluctuation in the background will be square root of that. And if we do that, this is where now the background also comes into picture. So the T half limit on the observed T half will be something like this. So because Na is Avogadro number, so Na, mass and isotopic abundance, this actually gives you just the total number of the NDBD target nuclei. This is nothing but a dN by dt is equal to minus lambda n. That's what it just recasted into that. Efficiency is your efficiency of detection efficiency. T is the observation time. Now what we have to note here is that what goes into getting your better sensitivity to get T half larger and larger, you need to have low background events and low delta I, low resolution. Earlier we very clearly saw that you needed delta I small to see a sharp peak, but because you are also have to be clear over above background, improving background is something which is also very crucial. And I'll now give you some example when we look at it, that how this over the years actually this a lot of effort has gone in achieving much lower background that has improved the sensitivity by orders of magnitude. So what's the present status? As I said, the normal double beta decay has been detected in about 13 nuclei and half-life measured. One of these cases actually EC. And improvement in sensitivity has been achieved because of background reduction, and we'll talk about some examples, but no NDBD has been observed yet. So in the last 2 decades, there has been a more intense effort, especially after seeing the neutrino oscillations. Even earlier, the people were pursuing it, but that kind of put this experiment on a high priority. And when there are experiments with a few kgs or few tens of kgs, people have been able to reach the half-life limits around 10^24 years. And now there are experiments which are ton scale, and some data from that is there, and we'll see where we stand. Now, anytime you talk of rare event, the background reduction from the experimentalist point of view is very, very important. This is exactly like saying if you want to hear me and if the room is noisy, you won't be able to hear. So what you will do if the room is noisy? One of the things, you will shut the windows. So in this case, when we are looking for the events in the, trying to detect electrons in the double beta decay, the background is coming from where? The background is coming from everywhere, the material, cosmic rays, because the reactions from the cosmic rays in the material itself. So first thing you do is you want to reduce the cosmic ray flux, so you go underground. So all these experiments happen at a good depth to look at the thing. Second is you make a careful choice of materials, because your material has to be radio pure, plus it should have very less residual radioactivities like environs. If you take any brick, if I just take a detector, say a gamma ray detector, and put it here, what do you think I'll see? I'll see any activity. There are no sources around here. Do you think I will see any gamma rays in this room? Yes? Yes or no? Only 2 possibilities. Maybe also is an answer. We'll see, because when we have the concrete and bricks around us, there are uranium, thorium, trace elements are there. And normally those, they have a very long half-life when we talk about, because that's like a 10^9, 10^10 years. So if I'm doing an experiment, say with an accelerator-based experiment, whatever I look at is much shorter half-life, and they will have much higher count rates. But now you're comparing, when you want to study something which has 10^24 years half-life or longer half-life, this is a much faster. No? So even all the background which is coming from these so less probable events also becomes very crucial for you. And if you, I'll show you some spectra later, that in the natural radioactivity, highest energy gamma ray which you observe is 2.6 MeV, 2.614. And that is the reason I said that if you have the Q value above 2 MeV, it is preferred, because then the background due to the natural radioactivity can be reduced. It's better than 3 MeV, is even better. So you also have to make clever detector designs as electronic rejections for background events. The other challenge is to minimize the neutron background, because neutrons are everywhere. You last talk you heard about dark neutrons. So I'm right now not worrying about dark neutron background. We are just looking for this neutron background right now. So where do the neutrons come from? All the muons, as they pass through various materials, they generate neutrons, and they're fast neutrons, but they travel through various materials and will slow down. And uranium and thorium, whatever trace elements they are, they undergo fission and they also have alpha decay. So these alphas which come from uranium, thorium also make reactions on light elements like silicon, magnesium, sodium, which are around, and then generate neutrons, and fission of course generates neutrons. So those are the things which you have to really take care of. So this is not a very comprehensive list, and oh, I'm sorry about this white thing. Yeah. So basically there are a few experiments which I have listed looking at different isotopes, and I picked them up for the just to illustrate that a different kind of techniques which have been put in. You know, the initially people started with calcium 48 because that has a highest Q value and it will be a very nice, fastest double beta decay you'll expect. But because it's low isotopic abundance, it's difficult. And then people jumped into germanium because the germanium is, you can make a very high resolution detector. And in the meantime, actually the EXO and more so Camlands, and they actually had set up the detector for reactor neutrino experiment. When that was over, they just made a xenon loaded liquid scintillator and they improved the background. So what finally goes into the product in the T sensitivity is B delta E, right? Background and the resolution. So they achieve a much better background. So today the best limit is actually found from Camlands. So as you see, these all have a very high, reasonably high Q values. And they also use different techniques. So either you have a semiconductor detectors, which is like a diode. So there is an energy gap, band gap, and the incident charge particle deposits the energy, which is converted into the, which leads to the excitation of electrons. There are also EXO puts the TPC, which is a standard detector segmentation, and the combination of ionizations and scintillation detectors. There are superconducting bolometer detectors. This is something which are, I should also mention, most of the detection technologies which are used are the large size detectors can all easily be used for the dark matter, and many experiments try to do both the things together. So I will try to give an example of each of these detector which is. So let me start with germanium because there was around 2010 there was a claim that in germanium NDBD was seen. So Garuda was set up for that. So this is a germanium detector located in Gran Sasso. So this is a kind of to give you an idea of a detector. This is a person standing here. So normally a germanium detector in nuclear physics is used in a single cryostat. You cool it down to liquid nitrogen temperature to remove the thermal excitations, to minimize the thermal excitations. So here, what they did was, I mean, that's the kind of a novel thing in each of some detectors introduced, and I'll try to give a flavor of that. That germanium has to be cooled. They use liquid argon instead of liquid nitrogen to cool it. So now this liquid argon itself acts both as a detector coolant as well as a shield for neutron. And this is surrounded by a water Cherenkov to get the muon Vito. The germanium gives you an advantage of that you can have a segmented detector, so you can even have a large sector with segments, so you can have a more localized interaction points. And the pulse shape discrimination can be done because different particles will give you a different kind of reaction. So you can pulse, so you can, from based on that, also can discriminate on the background. The energy resolution, as expected, was very high, 0.15%. The expected background index to be 0.02 counts per keV per kg per year. This is in the region of interest. And I think they didn't quite get that, but still, this was fairly good. This one ran from 2013 to 20, and they have put a limit, and this one, Garda is no longer running. Moving on to the 136 xenon. The EXO 200 was the prototype which was done. This is located in the waste management site in the US. This uses a liquid xenon time projection chamber. So in that sense, for the TPC, the media is also provided by xenon, and it is also uses 80% enriched xenon isotope. So, but because the TPC with the electronics and scintillator, so you have a both ionization and scintillation signal from the TPC and there, and then you also get an electronic rejection of multi-hit signal. So now you look at their background. It's order of magnitude, at least order of magnitude better. It's 0.0017. All the units remain same. And this also has stopped running now. In 2019, they published the data with 234 kg year exposure, and they put a limit of 3.5 in 10 power 25 year with a effective neutrino mass in about 80 to 240. Actually, originally when this was proposed, they had second step to it, because the xenon, when it decays, it goes to barium, and barium has a metastable state. So the idea was to have a laser excitation on the barium. So when you get an electronic signal that you have a double beta decay, shoot your laser on the barium, excite it, and do that. That would have been a very positive identification. Some tests were done on that, but I think right now there is not further on that. But they have the next step called NEXO, that is the 1-ton experiment plant. Camland-Zen, as I mentioned, was this scintillator detector, which was used for reactor neutrinos, and they went and added xenon to it. So they could actually put close to 400 kgs of xenon, and they had already an excellent background suppression and so on, but they still initial stages had some silver impurity. So they got rid of all that. They managed a 91% enrichment. The resolution was poor, 4%. But overall, if you look at the background which they achieve because of the background reduction, they get much better. And their first two phases itself gave this time limit after the purification background, and their final result is even much better. Kuare. This is the tellurium, which I told you had a 30% enrichment. So in this case, one could think of using a detector without enrichment, and so they started with that. This was one of the largest bolometric detectors which they started with. So here there are multiple crystals arranged in an array, and you cool it down to 10 millikelvin, which is very similar to something, the Tintin idea is very similar to that. And here also the expected, goal on the background was 0.01 counts per keV per kg year, and they expected to get a 40 millielectron volt sensitivity. So, but here they use a lead shielding, so there is a huge mass which is cooled to 10 millikelvin. And this I want to show as a next generation germanium experiment which is going on, and this has improved on Gardner. This will go to a 1-ton scale germanium. Most of the people, as I say, that all the germanium on the earth will actually go into the, all available will go in this experiment. You will have a difficulty in buying germanium detectors otherwise. The experiment says the large enriched germanium experiment for NTBD. And this is done in a, being done in a phased manner. That Legion 200 with 200 kg is actually running at LNGs. And they have gone into the further, not just the enrichment of germanium, the purification of cryostat, the purification of the liquid argon, which is used for cooling. All these things are done to improve the sensitivity. And what do they expect? They would expect to see about 4 events. I think you can't read that, but about 4 events after the running for 10 years. And so that's the goal right now. But what they have is they have actually achieved the proposed goal of doing 10 minus 4 counts. So this is now one more 0.0002 counts per keV per kg per year. And that's where they expect to get a sensitivity of 10 power 28 years. So it's like they should be able to hit the bottom of the inverted arrow. So what are the best limits so far? Since Gerda ran for 10 years, I would like to quote from that. Yes, in final result gives about at 90% confidence level, 1.8 in 10 power 26 years. Camland-Zen gives 2.3 in 10 power 26 years, and Core give 2.2 in 10 power 25 years. These are various available. I just want to mention in passing that there are also the direct neutrino mass measurements. So like a Catherine, which is looking at a tritium beta decay with a low Q value, so change in the measurement of the endpoint energy is very can be obtained, and they expect to have a sensitivity of 0.2 eV. So that is going on. Mayer is not running now, but Holmes Echo both are looking at the electron capture in holmium, which again has a very low Q value. So they expect to get lower sensitivity. So now coming to the Indian effort, what we are looking at. So about a decade back or a little longer than that, we started looking for NDBD experiment in India. And tin was thought of to be, we chose tin. So why we chose tin is because it has a reasonably high Q value. It has about 5% abundance, so it's again not very small. Now tin has goes superconducting at low temperature with a transition temperature around 3.7 K. Now what happens when it goes below superconducting temperature is this lattice specific heat which goes as gamma T falls off exponentially, and electron specific heat which is going as gamma T falls off exponentially, and only lattice specific heat will survive, which is T cube. Now if you are at a temperature below 1K, the T cube will be the much smaller, and hence you can make it into a calorimetric detector. That's one of the reasons the superconducting detectors are also becoming common, because semiconductor detector, the available materials are very few. When you are talking about for dark matter detection or any other, in fact today when people talk of quantum sensors, you have a wider choice of materials for making superconducting detectors. And in the you also the energy required for the exciting electron Cooper pairs is in milli electron volts. So your sensitivity and resolution is much better in the superconducting detectors. So you get a much higher resolution. From nuclear physicist point of view, tin has Z equal to 50, so which is a closed shell, and metallurgy is simple. For the tin, purification will be easier. What is known about tin is that the double beta decay half-life from the excited state decay measurements is about 10^21 years. Actually, even the normal double beta decay in tin is not yet. So what is a bolometer? As I was just mentioning, that it's a calorimetric detector. So the energy of the incident particle will be converted into thermal energy because it's going into the excitation of the lattice. And if the specific heat is low enough, it will give you measurable temperature rise. So you measure the rise in the temperature to and then deduce the energy of the particle. So what we need for that, you'll have some heat sink to keep it at low temperature. You have an absorber, or in our case like this itself will be a double beta decay detector. And there has to be a weak thermal link here. And you need some sensor or thermometer. And the incident energy, this is an equivalent circuit because you have two capacitors coming into picture and you have a pulse decay coming. So why is resolution good? Because now the resolution of bolometer is actually limited, in principle, in theory, limited by thermodynamical fluctuation noise. So this is a very, very small number. It depends only on operating temperature and specific heat. It's independent of the energy of the particle. All other detectors, when you see semiconductor detector, gas detectors, because the number of charge carriers created is proportional to the incident energy. So the resolution is energy dependent. Here you have it as an independent of incident energy. The challenge is that you really need to make measurements, pulse measurements at millikelvin temperature. Which you do, the Corey showed that it can be done. So now when we talk about a cryogenic detector, now you will see that we are not going to be talking just about particle or nuclear physics, but other aspects. So what all needs to be done? Firstly, we need sensors for millikelvin thermometry. You have to be able to measure that kind of temperature. We need to understand the radiation backgrounds. We need simulations. And then the first step is make a natural tin bolometric detector. We need nuclear transition matrix element calculations because the NTM is what is finally required to go from T half to your effective neutrino mass. When the Q value also needs to be precise, because if the Q value is not precisely known, that is another uncertainty which will go in your thing. So this is nowadays with ion traps, there are further directions in that. 5% is not a good abundance for a large scale detector, because what happens is we are looking at 124 tin. But the tin is one of the nuclei which has many isotopes. So it has 112, 116, 120 and so on. And each of these, all even isotopes have a probability of double beta decay, either beta minus or beta plus. Now, if you take subsequently the most neutron rich, this is something because if you look at the nuclear binding energies, it will be clear. Most neutron rich will have the highest Q value. Yeah, but as you go down, it will lower. So when you have 120 and 124 tin, 120 tin will form the background on the lower side of 124 tin. So I will be able to look at NDBD of 124 tin cleanly, even if these guys are present. But for the other nuclear lower isobars, I won't get that. But all these, when you have other elements present, remember you have gammas and neutrons in the surrounding. Whatever we do to minimize it, it is not going to be zero. They will be there. And those neutron-induced reactions will create a background field. So if I don't have an enriched tin, there will be reactions on 116 tin which generates indium 115, which will have a background. Whereas if I go for enrichment, I would then deal with background or the issues which are coming only from 124 tin, and I will get as much as possible remaining out. Now this we tried doing a laser-based isotope separation, but we didn't quite succeed in that. So this also has to be done in centrifuge. So I put that in the red because this is someone will definitely will have to go back to Russia. Most of the double beta decay experiments which you look at enriched isotopes, all of them come from Russia. And we need to get reliable NTMEs, so that requires additional measurements for constraining the transition matrix elements. So as you can see, if you look at different aspects, this is a very strong multidisciplinary project. There's nuclear physics, there's neutrino physics, which is obvious. But when we go for the millikelvin detector, there's a low temperature physics, there's a material science and physical chemistry also. And of course, engineering is there because you have to make this large size detector. So the specific challenges now to coming to the 12014 cryogenic bolometer are also the thermalization issues. Because when people usually do these low temperature bolometers, they do it out of insulator. Because the insulator, again, just the low temperature specific heat is going as a T cube, so it is a small thing. But in case of superconductors, there is a slight issue between because there is a decoupling in electronic and phononic system, so you don't get a full energy deposited. So there are studies which you can do. So this also, people have also explored the single crystal versus polycrystalline, because there are polycrystal has more boundaries. So there are scattering of the boundaries and so on. But finally, I think this is right at this point not very conclusive, which will give better only when you go to large size you will see. The other important aspect when you for all these bolometers, or when you talk of such low energy resolution, low temperature, is the vibration effect. Because whenever you isolate keeping something at a millikelvin temperature and you are sitting at a 300K, there are lots of thermal isolation stages. You can't have a wire just running, so your readout wires are long, they are anchored at different stages and so on. So because of these long wires and the whole mass is sitting at a very low temperature, any small vibration will give to the heat will be picked up by the detector. So that again becomes a noise for the detector. Additionally, tin has a problem. Some of you may have heard of a tin paste problem. And there is an allotropic transition not at millikelvin temperature, but at low temperatures, it can go from beta to alpha, so it just powders when it comes in because of the to this sudden increase in the volume in the transition. So you don't want to be making a ton detector which has to run for 10 years, but you come back after 6 months and find it's all gone into powder. So we had to arrest that. So we had to also look at various aspects. So what we have done in the past few years is have looked at many of the aspects which we can see. So this is a cryogen-free dilution refrigerator installed at TIFR, and this is where you can achieve a base temperature of 7 millikelvin. So what you actually do here, without going into details, is you use a helium-3, helium-4 mixture, and with a clever combination of that, you get a low temperature. If there are questions about it, I can discuss that in depth. So as you see, this is the final stage where it goes to the coldest, which is a 10 millikelvin stage, and then there are all various intermediate stages. So you mount your detector here and do the measurements. Now, for the first thing is when you want to make bolometer detectors, I need a thermometer to measure the change. And what we will look at is some change in physical property, which will have variation with T. So what we chose was the neutron transmutation doped germanium sensor. Here the resistance R changes with T, which is given here. And it is exponentially, so it's ultra sensitive. So what we do is you take a natural germanium, irradiate it with thermal neutrons, and so given the natural abundance for different, so sometimes you have small variations, you'll make the products, and after the final decay, you get this product. So you get a final doping into the system, and depending on the net, since this is the dominant, you will get this is the most N-type doped. Because of that, now you have made the sensor where you can control the R. What will happen if I don't dope it? If I have a pure semiconductor, as you cool down, the resistance becomes too high. So with doping, you're actually bringing the resistance in the measurable region. So if I put a very high concentration, like 10 power 19 cc carrier density here, then it will become metallic. And if I have it less than 10 power 16, then it still is not in a measurable range. So you have to achieve this level of doping, which cannot be easily done by chemically, so but you do it with a neutron transmission. But you take a piece of a sample which you want, you go and put it in a reactor, and we want to have a low background. So it doesn't come out clean. It will come out dirty because there are low energy neutrons, there are high energy thermal neutrons, high energy neutrons, everything. So you have to get rid of all the things that happened, undesired thing happened. So what we found was that there were a lot of, so first thing we do is you bring out a sample and do a radioactive purity studies, and we had to estimate and cool down period of 2 years, which comes in for these samples. First, there will plus there will be fast neutron induced effects, so that because the germanium crystal also has to be good to be able to get that R variation, consistent R variation. So we had to work out a fabrication recipe that you first annihilate and cure the defects. This was all verified with various standard techniques like channeling and positron annihilation lifetime measurements. And so some of the INO students did all this. This is work of many students which comes in. Now then you get into the sensor fabrication. Now the surface again needs to be shiny and clean, smooth to avoid the leakage path. So you have to polish the crystals after they have been come out of a reactor. You have to etch them because the surfaces seem to have some additional radiative impurities. So all that is done. Then you put a mask on a wafer and then make the wafer. So this is like your condensed matter or nano device fabrications or even semiconductor device fabrication techniques. So we took a lot of help from our semiconductor colleagues and did that. Then you make the contacts with the germanium gold alloy wire. So the first thing when you do with a sensor is check the VI characteristics, because having a good linear VI characteristics at low temperature is a state of the art. It doesn't happen on every piece which you do. There's a lot of rejection. So that's something which you come, and then you also work out your binding and the contact making procedures based on that. So this is why you see a blown up area for the close to the origin. So, okay, good. We have a good sensor at least. Now you go and test it. So you know that, as I said, that the resistance is expected to vary as R naught exponential T naught by T to the power alpha. Does it actually the sensor behave that? That's the first thing you want to change. R naught is the property of material. T naught depends on the doping level, and the alpha is nearly 0.5. And we find that yes, indeed the sensors which we made from different batches, the DGE just show different dopant levels. We get that, and we could make the good millikelvin thermometer. So then next step you go is that you also have to improve the contact making on the sensors, and we found that what gives us a better linearity even down to about 50 millikelvin temperature. Ultimately, we still have to go down to 20 millikelvin, but these sensors now are found to work good to 20 millikelvin. Now, we have to learn overall the noise. This has a, because once you have a vacuum system and you have a cryogenic system to cool down, they all have own vibrations and things, plus our lab is on the first floor, it doesn't help. Ground floor and the basement labs help. So we had to understand all the noise characteristics. So we did with a sapphire bolometer. So we mount in silicon heater and first check the phonon pulse response to it with these different sensors. So these are the observed pulses. So we see a good linearity, we see a good resolution, but we do not get a good resolution yet with the alpha particle source. So it needs an improvement. So the first factor which we found limiting was the noise. And we have gone further to see now understand the noise. So there are two things which you have to do in case of noise. One is that we need to put the preamplifier stage at low temperature, because then the cable capacitance and effect gets reduced. So that's being designed. And since these sensors itself, now we are talking about germanium resistance, is in the gigaohm, is in the few hundreds of megaohm to gigaohm, because it's going exponential. So something which is a kiloohm at room temperature, as when it goes down, will become that high. So we designed this low temperature preamplifier with a very clever input specific FET pair, and we have to use a differential amplifier readout. I'll go through some of this part quickly, and if there are questions, I can answer later. And analytical noise model was developed. So you see the contribution in the noise, because you have a sensor resistance which is at a gigaohm, as I said. So you have a Johnson noise from the resistors. Then you have an amplifier, current density noise, and the voltage noise density white noise. So what we showed was that the most dominant source for the range, our range of interest, is at a below 100 millikelvin is actually the current noise density of the amplifier, and the resistance of the sensor should remain below 1 gigaohm if we don't want the Johnson noise to become a dominant factor. So now after the understanding the noise and the low temperature development, we are back to the bolometer measurements. So now let me go over in the next 10 minutes with the other very crucial aspect, which is the radiation background. So as I told that any surrounding has the uranium, thorium, and all other backgrounds coming in. So we made a low background setup in our lab. So this is a germanium detector, which is with a carbon fiber body, which is again better from radio purity point of view. This is surrounded by high purity copper and then by lead. So lead copper offers what is called a graded shielding, because the radiation created in lead gets absorbed in copper. This is a Roman lead recovered from sunk ships from the Roman era. So this way there is an isotope of lead which has an 30 years of half-life of alpha decay that has completely vanished. Now, if we, in addition to that, the whole thing is enclosed in a perspex box and we purge it with nitrogen to get rid of the radon which comes from uranium chain. And this I'll show you that how much changes you see here. For example, this is the normal spectrum. The moment you put all this shield, you have all the carpet has substantially reduced. And further, when you put the veto, the carpet also reduced, but you also see some changes in the lines of interest. So let me just quickly show you these are the three main natural chains: 232 thorium, 235 uranium, and 238 uranium. So if I look at isotopic abundances, 235 uranium is very small. So for the today's discussion, let's forget that and look at these two chains. So 232 thorium has a first stage of decay 14 gigayear, and after that rest all is much smaller compared to that. So what you get is kind of a static equilibrium at this point. But this one ends in 208 lead. And this is the last transition, thallium to lead. This is the first excited state in lead, which is 2.6 MeV. But on the way, it emits various alphas and betas. Similarly, uranium-238 has a lot more beta decays, and it will again end in the lead isotope. So here you have a 222 radon decay. So if you look at this line, which is coming from the bismuth isotope, this is present. And after you do the nitrogen flushing, you can see that that line is gone. And you can actually see that if you have a 15 days data, 1 month data, and so on, that it reduces. And that's something which is important, because otherwise that stagnant background builds in. And we are interested in the region near Q value, but the low energy background can also pile up with something, can add and give you the background. And low energy count rates are much higher compared to that. If you see in this, yeah, the low energy things go back because of the comp. So what we, So just want to show that, so we use a boil of nitrogen from liquid nitrogen cylinder so that you get a lot of gas, and that is passed through at a constant rate, just 10 millibar above the pressure. So once we made this setup, we wanted to qualify that whether we can really use, what is the sensitivity we can achieve with that. So we of course used even our sensors and other materials for checking radio purity, but we also looked at the double beta decay to the excited state. So suppose the 94 zirconium double beta decay can go to the ground state, but can also go to the excited state. If it goes to the excited state, it will decay by an gamma ray of the 871 keV. And we will try to look for this gamma ray, 871 keV. Of course, we used a natural zirconium, and we are looking, the probability and the half-life for this will be slower, definitely slower because of low Q value. But we could put a limit. We could, the earlier limit was about 1.3 and 10.19 years, and even from a sea level measurement, we could improve that limit by a significant amount. The other aspect which we have to understand is the muon-induced neutron reactions, and that in the material, both in the lead and other iron, etc., were studied. What we looked at is even just from here, for example, when we were looking at the tiles data, when we did zirconium, we had put zirconium plates here, and then we rejected the cosmic ray data and looked at only zirconium when you are looking at double beta decay to the excited state. But we could also look at the gamma ray spectrum in coincidence with cosmic rays, which allowed us to study neutron-induced reactions. And this also revealed something that the GIANT was not doing that well in the earlier versions. So our data provided a crucial input for the validation of the next level of giant. And this has also told us that how neutron-induced gammas with the lead, which will be, if you use as a shield, will have gamma rays going up to 8 MeV, even copper. The neutron-induced background in tin itself is of a concern because neutron capture in 124 takes you to 125 antimony, which has a Q value now higher than Q beta beta. And this is a single beta decay in 125. This has a 10 minutes half-life, and it has two states, 10 minutes and 10 days. So how do you take care of this? This is taken care by storing the material underground. So you minimize the exposure of the material to the cosmic rays. So like when we bought the Roman lead, we had to make sure that it came by the sea and not by the flight, because otherwise it would have created more activity. And in fact, all the germanium for experiments which has gone from Russia is always surface transported. But what is more worrisome is if you have a high neutron flux, it will have a sequential reaction, right? Because 124 can go to 125 and 125 can go to 126. Now 126 tin has a beta decay value of 378 keV, but has a long half-life if it goes to 126 tin. But 126 antimony has very high Q value. Again, so this will become in 10 power 5 years, it will become a significant background from the given 124 tin. So this is a concern, and we had to understand this. So some studies were done with this different neutron capture studies in both accelerated neutron beam and in the reactors. So the only thing in this case is that you have to minimize the exposure to the neutron. So store them in underground, also surrounded with hydrogenic material which will absorb neutron. Now this is an important aspect, the nuclear structure aspect, because from the, as I said, to get to the effective mass, this is a crucial input. And today there is a large uncertainty because there is a lot of model dependence which goes into that. So there are different ways how it's calculated is mostly it's a shell model and its variants. And there is actually there is a lot of theoretical effort in TMA calculations in India even before the experimental activity. The groups in PRL, University of Lucknow and IIT Kharagpur, Ropar were doing that. So what we can additionally do now is that do the reaction studies like DP, PD or the gamma-Teller transitions which are there, and these will provide some constraints in the states in the calculation. This becomes useful in reducing the uncertainty. There's also now, this was earlier today, in fact, in some nuclear they claim that they have achieved it better, like a factor of 3. And recently this work was published from IIT Ropar as also, which was a thing also part of the tin. Now I talked about the tin pest problem. So I have another 10 minutes or 5 minutes? 10 minutes? 5 minutes, okay. Yeah. So I'll go a little bit quickly through this. So in the tin, since we said we had to arrest this beta alpha transition, you can alloy. You can easily alloy with lead or indium, but some of these things we wanted to avoid. But finally we found that the bismuth gives the best alloy in terms of stability and without disturbing superconductivity. And bismuth was thought to be stable till about 10 years back, but now we know that bismuth has an alpha decay with a 3 MeV alpha transition, and the half-life is like 10 power 17 years, I think. But when you put this, we have to now assess the impact of its radiation. Now, in general, not just in tin bismuth, even in most of these detectors, one of the major source of background is like either in germanium or in tellurium detector are the surface events, which is illustrated here. Because when you have alpha and betas, which are, alpha particles are decaying, alpha have a unique energy. So why does a 4 MeV alpha become a background for the double beta decay measurement of the region of interest is around 2 MeV? Is if the event happens inside the detector, full alpha energy is deposited. But event happens close to the surface, only partial energy gets deposited. And then it will come in your region of interest. So this is shown for this bismuth, that you will have either 3 MeV alpha or 2 MeV, but if the alphas are emitted close to the surface, then that will generate the background in the region of interest. So in fact, many of the experiments like Core have spent a lot of effort in having the pure crystal of getting rid of the alpha impurities. And they have further gone to things like scintillating bolometers, which I didn't talk about Lucifer, because they are then looking at both because when you're looking at temperature rise, you're looking at a phonon signal. If you look at now the scintillator light, then you get a photon signal, and that is different for alphas and electrons. So by a combination of phonon-photon signal, you can get rid of improve the background further. So we did some simulations and showed that we need about 0.22% of bismuth, but even at 0.25%, the background is handleable. Now here again, the size of the bolometer becomes an important, because if I have a larger size crystal, when larger I make a cube, say 5 by 5 by 5, then the surface to volume ratio is better. So I will have an overall higher efficiency. But if I have a bulkier crystal, bulkier detector unit, then the net temperature rise in for the energy deposition, because mass is large, will be small. So you need to make an optimization between the two, and 5 cross 5 cross 5 seems to be a reasonable size for that. So here we have some estimated backgrounds which are listed, that if you had bismuth, this is coming only from the bismuth alpha decays in the region of interest. And this is for the assuming the thorium, uranium impurities of this magnitude, like a PPT level, what kind of background we expect. So what you see is actually the bismuth will not be a dominant source. It's the uranium chain which has the lots of beta decays. So that is what gives because beta decay gives a continuous spectrum. So that is the main source of background. We have also carried out the radiation background studies for different rock samples. These are the sites, 2 sites for the underground laboratories which were thought of, one in the north at close to the Atal tunnel, and one in the south at the So we can see that some rocks are very rich in potassium, and the variation in the uranium thorium content is quite significant. So the uranium makes a lot of difference, because the fission is also faster in that. So this, let me skip. This is again evaluation of various sites for looking at that. So that more or less then brings me to the conclusions, that what I hope I have given you a glimpse of what all we have done in terms of looking for making a natural tin bolometer for the rare decay studies like NDBD. They're looking at different aspects. So what we want to go merge on further is, okay, make measurements with natural bolometers, and anti-germanium sensor of course continues. We are, I showed you an example of a double beta decay to the excited state, which is 94 zirconium, but we are now looking also additionally at 96 zirconium single beta decay, because I remember I told you that's a spin forbidden, not energy forbidden, so it must happen. And so we'll try to look at it by looking at a gamma decay. The projection for the tin detector, again, if you do it like all others, we have to go in a phased manner, but if you had a 1-ton detector with about 90% enrichment, achieve the background of, this is a very crude estimate of background. We hope with all the techniques you'll be able to do better than this. You can get a sensitivity at this level. And these are all various people involved in it. These are mostly the students who have graduated and gone to different places. I'm very happy to tell you that both these students, Harishri and Aparajita, are currently working on Legend. Some others are working on the dark matter. So these are all the happy group. And thank you.
Thank you, Vandana. Questions?
So at the Q value, there will be events present from both 2 neutrino, double beta decay and 0 neutrino. Whereas the lifetime we want to measure for 0 neutrino will be if we can single out that these many number of events are for 0 neutrino. So how do we differentiate between the 2 neutrino and 0 neutrino events at Q value?
Just if you are not doing neutrino detection, because that's 2 particles only, because in either cases you are only detecting 2 neutrons, 2 electrons. So there is no way to do that. But you, if the nuclei of interest where you're looking at it, you do the 2 nu beta beta, which is much faster. So you do that study, so you know that background from all other time which is coming in. So you extrapolate that end part from, because if I measure the complete 2 nu beta beta spectrum, then I extrapolate it to the end, because that's basically a phase space. So you extrapolate from that, but there is in the rates, the 2 matrix elements which also go in for 2 nu and 0 nu, they are different. But in the experiment, in the spectrum, 2 nu beta beta from the shape will be extrapolated, because so you have to do a careful, complete measurement of 2 nu beta. There you need to do electron angular distribution also, which is coming in. And that is much faster, no? So it is always coming in, but the numbers which will go in that are, the number is diminishingly small. So if you see some sizable events from that, that will come in.
I have one more question. So due to the, let's say, rock and other things which are present around the source and the detector, there are the backgrounds from these things. So if we use the passive detector technique and maybe use, for example, detectors like Kamiokande and put our source in between, so we can have a kiloton scale kind of detector, and we can, the water which is used in Kamiokande is ultra pure, so we have a good control of what the background can be, and we can remove those other unknown sources, or maybe known but I mean irremovable kind of sources of background.
So this is what actually Kamland Zen did, right? They had a neutrino detector setup, so they had a full large size scintillator.
Yeah, exactly.
Because when you say scintillator, you have this huge water container, then they have a further water shield, and all this light is seen through the photomultiplier tubes. Now photomultiplier tubes have glass. Glass has silicates, so it has potassium, silicon, everything. So if we today try to set that up, you first have to get all of that radio pure. So that's also when the possibilities are there, that kind of detectors are not. So when you talk of scintillator, you have to read it with PMTs. Now, in fact, people also try to read it through the silicon photodiodes, which are coming in, because that then offers a better control on the radioactivity, which is there.
Talked about this neutrino-less double beta decay versus the 2 neutrino double beta decay. So you talked about one is that there would be a peak, but can we also use the fact that for neutrino-less double beta decay, the electrons would be back to back almost, and the for neutrino 2 neutrino double beta decay, the it would be back to back, but also there will be a distribution.
See, that's a good point, but that can happen. It depends on your type of detector. If you are doing a TPC, you are doing the electron trajectory. If you are doing inside the, say, a bolometer or a germanium, you don't have the electron trajectory. You only know that in the big sample, so much energy came in bolometer. If I at least use a segmented detector, that's against the event reconstruction or trajectory can happen before that. Because you see, these are 2 MeV total Q value. So you have 2 electrons of approximately 1 MeV each. So the range is very small in the material. So, but if I have a TPC kind of detector, because I will know where it is hitting, I can do the trajectory. That is the advantage in TPC. In fact, in the previous generation of experiment, there was a NEMO, which had MWPCs, and they took the thin foils of the large detector. That's the another point, that if I do a passive source, the target foil has to be so thin that electrons have to come out of it. And then to achieve ton scale mass or very large mass with that is that you have to have long foils. But if you have a tracking, you can do that.
See any other questions? So let's thank Vandana again.
Thank you.